Well, it seems to be live because it's saying in broadcast, you know, and it says it's going. Okay.
Hi, everybody. Welcome to the Pyramid Science Foundation's live stream. My name is Lisa Richards, and we have Charlie Ziese with us today.
Hello,
Hey,
everyone.
Charlie.
It's great
Do
for
you have
both
any
of us to
announcements to
be
start
back
off with?
home from our trip.
Oh, gosh. Absolutely. And I'm sorry if I'm kind of choppy. I'm having some issues with my internet today. So luckily, you don't have to hear much from me. Charlie's going to be our amazing guest speaker today. So you'll get to hear from him all day.
Well,
Did you want to
hopefully,
start with any announcements, Charlie?
I was just going to say it's great to be back. Lisa and I were out in Cincinnati over the weekend. We met some wonderful people there at the Body, Mind, Spirit Expo in Cincinnati. Um, Lisa may want to comment on that. I'm going to, about the experience itself, but we hadn't been there. Lisa had been there a couple of years ago, I think, before COVID, and quite honestly, we we didn't get the greatest. Well, we didn't get very much in the way of listenership for my speech. Number one, we didn't see, but we met some great people, and but we also didn't make very much in the way of sales, and so it was somewhat of a disappointment. And I'll just kind of let you speak to it for a minute before we get started. But go ahead. Are you there, Lisa? I think she's. I think we're losing her. So I think I'll just go ahead and Lisa told me her reception is iffy today. So I think what we'll do is just go ahead and start with a presentation. What I've done for today, a lot of the information that I'm going to be presenting today is new. Um, I've just done just in the last week or so, a lot of new research into finding these powers of phi geometries uh, in contemporary architecture as well around the world. And I wanted to show you that as well as the information that I provided last weekend. We're also going to be, for the first time, discussing some of the information that we're just beginning to research on uh, how these powers of phi geometry may relate to uh, higher dimensions. And so that's going to be the other subject that we haven't really discussed before in great detail. I'm going to show you that as well. So we've got lots to do, and so I might as well just open up and get started here. If any of you, let's see, let me,
You'll have to open it again. It shut down.
okay, yeah, there we go. Can everybody see that now?
It looks good on our end or on my end.
Okay. All right. So I've modified the title of the presentation to include contemporary architecture now as well. So what we're going to be doing first is discovering the golden ratio in Gothic cathedral steeples, and then contemporary architecture, and then finally we're going to end up discussing orientation of perspective and how the information that we've gathered from the Gothic cathedral steeples may be leading us to an understanding of how they relate to multidimensional, hyperdimensional geometry. So just to start, this is a cover page, and we'll be using this to try to get across some of the basic concepts of how the powers of phi geometry works. In summary, when I last fall went through all of the Gothic cathedral steeples, I determined that there were 6 basic geometric angles, and we're showing them here starting on the left and going to the right, you can see that with each one of these, it gets steeper and steeper and steeper in terms of the geometry. So what we're going to be talking about in the first half is how these six geometries ended up, or I was able to determine their relationships, and it all has to do with the powers of the golden ratio. So, just by way of introduction, Gothic cathedrals are religious buildings constructed in Europe between the mid 12th and early 16th centuries. Many people consider these structures to be the most beautiful and breathtaking architecture ever constructed. One of the most prominent yet poorly researched features of these cathedrals is their magnificent steeples. Until I discovered the universal Phi scaling angle of 76.345 degrees in the Gothic cathedral, in a few of the Gothic cathedrals a few years ago, there really wasn't any research available on Gothic cathedral steeple geometry. And that's surprising once you see the results, because every single one of these steeples has the golden ratio contained in it. I did do research with some church seminaries, and just to make sure I wasn't missing anything. And the research librarians indicated that there was no research available on these, which is very surprising, or will be once you see the results. But anyway, I was able last year to decode all of the Gothic cathedral steeple geometries, demonstrating for the first time, at least since they were originally built and we lost this information, that these steeples are all based on a very precise and sophisticated understanding of the golden ratio. So we're going to be showing the basic mathematics and geometry behind that, and contemporary examples of these geometries in religious and secular architecture worldwide and in the United States. And basically what this will demonstrate is that planet Earth is truly an open-air architectural museum of the golden ratio. So after you see all of these examples, I hope that, like myself, once you see this, you can't unsee it, and you're going to know that you live in a world that's not only demonstrating it through its architecture, but as we've seen from my other research, that it exists equally as robustly in nature as well. So, all right, what's the golden ratio? Most of you are going to know this by now, but the golden ratio is the ratio of a line segment cut into two pieces of different lengths, such that the ratio of the whole segment to that of the longer segment is equal to the ratio of the longer segment to the shorter segment. So to look at the box inside, A plus B, the whole line, is to A, the larger or longer segment, as A is to B. So that's the relationship. The golden ratio, or phi, is the only solution to this equation, and we approximate that as 1.61803398887 ... This is an infinitely irrational number, and that means that we can only approximate it, but that we do approximate it as phi, or the golden ratio. But this specific number, therefore, because of its ability to scale, it makes the golden ratio nature's natural scaling ratio. Now, what is universal Phi scaling? Nassim Haramein's research, as well as that of Dan Winters on the right diagram, they both demonstrated that the universe uses the golden ratio, or phi, to scale all three-dimensional objects from the subatomic to the galactic. And this research demonstrates that the universe uses a very precise methodology for organizing matter and information that is based upon the golden ratio. Now, unfortunately, neither researcher went on to develop a model of the geometry and the process that's involved with universal Phi scaling, but that's something that I have spent a considerable amount of time researching over the past few years. And this research resulted in the development of a consciousness-driven model of the organizing principles of the universe in late 22, which links the Fibonacci series, universal Phi scaling, a process that we're going to talk about called Phi convergence, the torus, and fractals. So we've got a lot of things that have been built into the model. This is the first time that this kind of a model has been put together, to my knowledge, before. So we're going to get through some math concepts here first so that you can get an appreciation of why the golden ratio and the Fibonacci is a derivation, actually, of the Fibonacci sequence itself. So the Fibonacci sequence, I'm sure most of you have heard of that, is a recursive formula. X sub n is equal to xn minus 2 plus xn minus 1. Well, that's just math speak for saying that for any number you in this series, you want to add the two previous numbers before it to get the new result. So when we use 0 and 1 as the first two numbers in the sequence, we calculate the Fibonacci sequence to be 0, 1, 1, 2, 3, 5, and so forth, as shown on the page. Now, the important concept to come from the Fibonacci sequence is the process of what's called Phi convergence. And what that is if you take those series of numbers, and we're going to leave 0 out of this next step because you can't divide by 0. But in order to discover Phi, or the golden ratio, we can take the Fibonacci series and divide each number in the series by the preceding number. Thus, the first ratio would be 1 divided by 1 equals 1. And if we go down and look at the graph at the bottom of the slide, you're going to see that first division of 1 is where my cursor is pointing. Now, the key thing to see here is Phi itself is above there, above that first dot, and is at the point of 1.6180339. ... Now, if we take the second set of numbers, 2 divided by 1, then we get a plot up here at 2. Now, you'll notice that the first one was at 1, the second one's at 2. The 2 is above rather than below the first estimate, but you can see it's a lot closer to 1.618 than 1 is. So we do the same thing for the third set of numbers. 3 divided by 2 equals 1.5. This time, we're below 5, but we're getting closer to it. The next one, 5 divided by 3, is 1.666, so it's slightly above. But you can see what's going on here. We're rapidly closing in on that hypothetical value through alternating estimates, which are one time above and one time below the actual ratio itself. And this phenomenon is known as Phi convergence. So this is one of the classic ways that we can derive Phi itself, is by using the Fibonacci sequence in this particular way. Now, just to talk about Phi convergence and universal Phi scaling for a minute, there's some prominent researchers out in this field that have the mistaken impression that you can only achieve this Phi convergence phenomenon using the initial number pair of 0 and 1, but nothing could be further from the truth. In fact, any initial number pair can be used to achieve this Phi convergence phenomenon. This is an important understanding because it opens us up to accepting the Fibonacci sequence as the perfect mathematical formula or model for universal Phi scaling. Now, I just want to show these briefly, and then we'll get into the main crux of what we're going to be talking about today. But we can start with different values of the first two numbers in the Fibonacci sequence, but yet we're going to be able to see that in very short order, any two number pairs will converge to the 1.618. And in fact, within 24 iterations, they all match up within with 8 significant digits after the decimal point. So to look at the yellow box, we start with a series of 0 and 1. You can see those numbers here, and you can see the successive ratios of the sequence that's derived, and you can see it rapidly evolves into the 1.618. We've got a second series of numbers here in the blue, 1, and I actually took a million as the second number. What's fascinating about looking at this, we're not going to spend a lot of time on it, but you'll see that the ratios that occur with 8 significant digits of precision are exactly the same, no matter whether we start with 0 and 1 or 1 and a million. So this is already giving us some conception that numbers and scaling can be involved with this whole phenomenon of Phi convergence. The third set of numbers, 500, and minus 50, you can have a positive and a negative number. You still get the Phi convergence phenomenon. And then finally, we had 2 negative numbers here, minus 50 and minus 10, and we get the same effect. Now, we're not going to go into scaling in any greater detail than to show you that the reason why the Fibonacci sequence is so good is because you can scale larger and smaller with it and achieve the very same results. So we took the same ending numbers that we had from the preceding page in each example, and now we've, rather than adding the 2 numbers together, we're going to be subtracting them, and you're able to scale downwards in precisely the same manner and achieve the same initial results that we had before. So what I'm telling you is that this formula, the Fibonacci sequence, achieves this universal Phi scaling phenomenon, and therefore I have done extensive studies of alternate techniques for achieving universal Phi scaling in nature, but this is the one that works. So with that said, I want to show you how we discover universal Phi scaling in the Russian pyramids, which is really the first place that I began to study sacred geometry. I knew that the angle was very close to the 76.3 31 degrees angle that we had as a rough estimate from a website called GizaPyramid.com, but I knew it did not incorporate the golden ratio. So the way that I was able to home in on the technique used to come up with the geometry of the Russian pyramids was through stacking circles, and you can do this in 3 dimensions with spheres. But you'll see right below the blue arrow here is the diagram. You start with a diameter of 1, and as you stack circles, in this case in 2 dimensions, on top of each other, you take the previous diameter and divide it by the golden ratio itself. So 1 divided by 1.618 is 0.618, then that becomes 0.382, 236, and so forth. You can do that to infinity, and you'll never reach the top of the pyramid. So this is an infinitely scalable process and technique. It results in the angle of 76.345 as the slant angle at the base of the pyramid and 27.309 degrees as the apex angle. All right, just a few more math things and we'll be finished, because this is important for understanding how I was able to get the rest of the Gothic Cathedral steeples figured out. And that is the links between the Giza and Russian pyramids. As I mentioned, the slant angle of the Russian pyramid is 76.345 degrees, and that's the one that shows up here with my cursor at the bottom of the large or taller pyramid, which is the Russian pyramid. Now, the Giza pyramid I have put inside here, assuming both the Giza and Russian pyramids have a base length of 2. Now, what happens when you draw the Giza pyramid, you notice, however, that the angle at the top of that triangle is also 76.345 degrees. So they share a very precise and common angle. But the most important thing for you to find for our purposes today is that the slant height, and that's from point C down to F, those two sides, of the Russian pyramid for a base length of 2 is 4.236 or phi cubed, and the slant height of the Giza pyramid is 1.618 or phi. So they are related exponentially, the slant height, by powers of phi. So with that said, now we're going to start to get into how was I able to figure that out. Well, as I mentioned in the previous slide, prior researchers had already determined that a Giza pyramid with a base of 2 had a hypotenuse or slant height of phi. Now, I'm going to be using both of those terms. The hypotenuse is really a geometry term. If you look down at the bottom of diagram on the right, you'll see that there's a right triangle that's been put in with blue dotted lines here. And that, of course, as all of us know, with a right triangle, the side that's opposite the right triangle is called the hypotenuse. But that also, in a pyramid context, happens to be the slant height. So I'm going to use both of those terms just to reinforce the fact that we're working with a right triangle, but that's embedded inside of a pyramid. So we know that slant height for a Giza pyramid is phi, and we know from my own research from the previous page that the hypotenuse slant height of the Russian pyramid is phi cubed. Now, what's important, significantly, I found that these very same geometries also exist in Gothic cathedral steeples. So knowing that, I decided I was going to do a complete kind of run through all of the steeples and look at all of them and see what I could find through an initial run through. And I found that in addition to the two geometries that we knew, the Giza and the Russian, there were 4 angles in addition. One that was intermediate in steepness between the Giza and Russian angles, and 3 others that were steeper. So just to summarize now kind of what I knew before I formulated my hypothesis, the Giza pyramid, which has the same geometry as the Gothic Cathedral steeple below it, has a hypotenuse or slant height of phi or phi to the first power. Now, we didn't know the intermediate angle, so I have a question mark there, but I did know that slant height or hypotenuse was phi cubed for the Russian pyramids, as it is for one of the geometries of the Gothic Cathedral steeples. And then we had 3 even steeper geometries, which I've identified with question marks. So, if you think about this in terms of what could theoretically be the missing numbers in this pattern, of course, it comes to mind that one thing we ought to try is the intermediate angle should be phi squared, and possibly the solution for the last 3 is phi to the 4th, 5th, and 6th powers. So that's exactly what I decided to test as a hypothesis, that the geometries of the Gothic Cathedral steeples are related by exponential powers of phi contained in their hypotenuse and slant height. And in order to do that, I used a calculator to determine the apex angles, that's the top angles of all of the 6 geometries. And then using a protractor app, I measured every apex angle of every steeple of every Gothic cathedral, as well as the major steeples of the 50 tallest churches in the world, all as defined by wikipedia.com. And I wanted to use an objective set of cathedrals so that people didn't think I was cherry picking anything. So I used all of those. And sure enough, the results came out that every single steeple, over 500 in total, conformed to one of these 6 powers of Phi geometries. So to kind of summarize this, we're not going to go through the math, but I just want to show you that when you use a pyramid calculator, and this one that I used is from a website, 1728.org/volpyramid.htm. But I ended up with these apex angles, and these are the apex angles that I used for purposes of measurement. And sure enough, when we take those 6 angles and fill in the blanks, everything fit perfectly. The phi to the first power of the Giza pyramid and the corresponding Gothic Cathedral steeple all matched up. The 44,914 we estimated to be the intermediate angle, proves out perfectly. Of course, the phi cube we already knew, and the phi to the 4th, 5th, and 6th powers all came out perfectly as well. So with every one of these steeples that I measured conforming to one of these 6 geometries, I knew that I had discovered a major find, something that really had not been rediscovered since they were originally built, and we lost this knowledge sometime in our past. So to give you some of these examples, this is the Rouen Cathedral in France. You'll see the phi to the 4th geometry in the left steeple, phi to the 5th in the center, and there's another one that has phi to the 6th. This is Mary Redcliffe Church in England. The major steeple has phi to the 5th geometry. The smaller steeples underneath or around the large one have the geometry of phi cubed. This is St. Mary's Church in Gdansk, Poland. All of its steeples have this phi to the 5th geometry, the major ones. And then there are some ancillary steeples with phi to the 2nd and another one with phi to the 5th. Bruges Cathedral in France. The main steeple is phi to the 4th, as are the smaller ones that surround it. And there's another phi to the phi cubed steeple geometry there as well. Now here's one from the Czech Republic. Very, very steep angle to the steeples, and they're both phi to the 6th geometries. Burgos Cathedral in Spain. We've got phi to the 4th, phi to the 4th, and some phi to the 5th and phi to the 5th geometries as well. Here's a Chalon Cathedral in France, phi to the 4th. Frankfurt Cathedral in Germany. This one has phi to the 5th geometries. Leon Cathedral in Spain. We have some phi squared steeples, phi cubed, another phi cubed, and phi to the 5th. Magdeburg Cathedral in Germany. You can see 2 phi squareds and a phi cubed geometry. Matthias Cathedral in Budapest, Hungary. A lot of different geometries here. Phi to the 4th in the main steeple. Some of the ancillary steeples are also phi to the 4th. The colored with a design on it steeple is phi to the 3rd, and the steeple next to it is phi to the 4th. Rochester Cathedral in England has phi to the 3rd, or phi cubed, in the main cathedral steeple, and has phi squared and phi cubed smaller steeples as well. Here's York Minster in England, phi to the 5th geometry, phi to the 3rd, and phi to the 4th. Winchester Cathedral, phi to the 4th geometry. And then finally, we're going to look at the Ulm Cathedral. This is the tallest church in the world. You see a main steeple here and 2 smaller ones in the back. The main one is phi to the 4th, and then phi to the 4th, for the two smaller steeples in the back. And here's a phi to the sixth as well. Now we're going to stop here, because we don't have time to go through all of these. But if you want a master presentation, we'll put this link into the comments section. But you can also refer back here if you'd like to see these. I put all of these cathedral steeples into a presentation on Google Slides, and I've got that available for the public to view. So you can go back and look at all those at your convenience. But now we're going to move on, because that's a profound discovery, and I really hadn't had time to do much research on other architecture until really this last week before the Cincinnati presentation. And in fact, I spent all day yesterday researching this as well for today's presentation. So we're going to find that there are literally thousands of churches, cathedrals, government and corporate buildings around the U.S. and the world that have these powers of Phi geometries. So we're going to look at some of those now. We're going to start in China. China has amazing contemporary office building architecture. So I wanted to show you some of those and show you that, the golden ratio is alive and well in China and many other countries around the world. So this is the Ping An Finance Center in Shenzhen, China. And we'll see that the top of its building has the Phi cube geometry. Here's a Shimao International Plaza in Shanghai, and it has the Phi cube geometry. Here's the Shanghai World Financial Center. We can see the Phi to the sixth. This actually kind of is changing. It's almost like it's changing dimensions, but at the bottom it's got that Phi to the sixth geometry. Menching Bank Building in Wuhan, China has the Giese pyramid geometry at the top, or the Phi scaled geometry. This is the Louvre, famous art museum in Paris. They built this contemporary pyramid. It's now called the Louvre Pyramid in Paris, and it contains the Giese geometry. This is a contemporary office building in London called the Shard, which has Phi to the fifth geometry. Now we're going to go into Russia. These are a number of buildings in Russia. And we shouldn't be surprised to see the golden ratio and powers of Phi, because Russia has known about this geometry and uses it in everything from their architecture to building their hypersonic missiles, which work because of, in part, understanding the golden ratio and Phi squared scaling, Phi cube scaling, whereas the U.S. Hypersonic vehicles burn up in the atmosphere because they don't use it. But anyway, back to the architecture here. This is the Lochte Center in St. Petersburg, and at the top it has the geometry of Phi to the fourth. Here's a residential building in Moscow, Edelweiss, and it has the Phi cube geometry. This is a stadium tower called the PFC CSKA Stadium Tower in Moscow, and we see the Phi cubed scaling geometry. We see another prominent office building in the background here we'll talk about in a minute. The Ministry of Foreign Affairs in Moscow. This building was built in the late 1950s. It has the Phi to the fourth geometry in its major spire. Here's a contemporary set of, I believe, residential towers in Moscow called the Vorobyevo Gory Towers in Moscow, and they have the Phi squared geometry. Here's the building I was referring to earlier, the Kudrinskaya Square in Moscow, again built in the 1950s. This has the Phi to the fifth geometry. Moving on to South Korea, Here's a Northeast Asia trade tower in Incheon, South Korea, um, with the Phi to the fifth geometry. This is another South Korea lot, I'm not sure, world tower, has the Phi to the fourth geometry. Moving on to the United Arab Emirates, this is the Uptown Tower in Dubai, Phi to the sixth. A tower in Dubai, Phi cubed. And it shouldn't come as a surprise that the United Arab Emirates, not only with their oil wealth, but with the extensive history of sacred geometry in Arabic culture, it's not surprising at all to find a lot of these buildings in Dubai with this geometry. So it's called the ICD Brookfield Place in Dubai. Again, we'll see the Phi cube geometry in that office building. Here's another tower, Business Central Tower, similar in many respects to the Chrysler Building in New York. It has Phi to the second, though, as opposed to Phi cube geometry of the Chrysler Building. Now we're going to go into the U.S. and look at some buildings and architecture here in the United States. This is a spire that was developed and built by Frank Lloyd Wright in Scottsdale, Arizona, and it has the Phi to the sixth power geometric angle. The iconic Transamerica building in San Francisco has a Phi to the fifth geometry. The U.S. Air Force Academy chapel in Colorado Springs has the Phi cube geometry. Here's a marquee residence, a high-rise residential building in Miami, has the Phi squared geometry at the top. This is the Bank of America Tower in Atlanta, Phi squared. Here's another Phi squared building, the Park Tower residential building in Chicago with the Phi squared geometry. Here's Trinity Church in New York City. I used to walk by this every day when I worked in Lower Manhattan. And the main steeple is Phi to the fifth geometry. The smaller ones are Phi to the fourth. Here's St. Patrick's Cathedral. When I worked in Midtown, I worked only really a block away from this church as well. So the two major steeples have the Phi to the fourth geometry. That's facing Park Avenue. And here in the back, we'll see there are two other geometries of steeples, one of which is Phi to the sixth and one is Phi to the second. Carlisle Hotel has the Ziese geometry of Phi. One Worldwide Plaza, a more recent addition to the skyline, has the Phi squared geometry. And then the new World Trade Center, One World Trade, has both the Phi to the fourth and Phi to the sixth geometries built into its architecture as well. This is from the new Hudson Yards area in Manhattan that was developed a few years back. 30 Hudson Yards has the Phi squared geometry at the top. 53 West 53rd Street in New York has the Russian Phi cube geometry in the top of its building. Moving on outside of New York, here's a Key Bank Tower in Cleveland. That's got that's not Phi to the sixth. That's my mistake. It's Phi to the second. So sorry for the mistake there in the writing, but I'll correct that. And then moving on to Philadelphia. This is a church that was very close to where I lived in Philadelphia, St. Francis Xavier Catholic Church. Phi to the fourth in the main steeple and in the smaller steeples as well. Here in Philadelphia as well, BNY Mellon Center. I've got the 76-345 Giza geometry here at the top of that building. Mormon Temple in Philadelphia. I walked by this to go home every day when I was still working on Wall Street, and those spires are phi to the fourth geometry. Um, I used to live close to this church in Pittsburgh, about a quarter of a mile from it, the East Liberty Presbyterian Church, Phi cubed geometry. Heinz Chapel at the University of Pittsburgh, Phi to the sixth. Um, Here's some architecture from Houston. The Bank of America Center there has the Phi squared geometry. Amazon began building this headquarters in Fairfax, Virginia, about a year and a half ago. I don't believe this building is finished yet, but it has the Phi cube geometry. Washington National Cathedral, all of its steeples have the Phi cube geometry as well. Pilgrim Congregational Church, Phi squared and Phi to the fifth geometries. This church is also known as the Old Stone Church in Cleveland. And here's where we were last week. I thought I'd show you a few of these. The Cincinnati City Hall has the Phi cube geometry in its main steeple or spire, and it has ancillary spires using the Phi squared geometry. And here is the Cincinnati Music Hall with, again, the Phi cube geometry. So you can see we're going to stop, looking at pictures at this point, but just the conclusions that we have to come to is that the builders of the Gothic cathedrals did have a very sophisticated understanding of sacred geometry and the golden ratio and used it to build all of the Gothic cathedral steeples. But somehow this knowledge has been suppressed, at least in the West, since their original construction. It brings into question, the validity of our historical narrative. How could all of these churches today say that they don't have any information? And I researched this thoroughly. But the Lutheran Church, the Roman Catholic Church, the Church of England, they all own significant numbers of these Gothic cathedrals, and yet none of them have any information on the sacred geometry associated with it. So it really does bring up a lot of questions about the validity of our history. So now we're going to get into the second half of what I wanted to talk about, which is the powers of Phi and hyperdimensional geometry. Now, my research into Gothic cathedrals indicates that they had this sophisticated understanding of orientation and perspective and how they relate to higher dimensional geometries. Now, we'll get into that. And we're going to look at some work from George Leoniak here in a minute. But what we're going to find is that hyperdimensional geometry can be brought into lower dimensions and into our 3D reality through perceiving those higher dimensional objects from the right proper perspective, orientation, or in our lingo, the proper point of view. So, just to kind of review this, if Phi scales in one dimension and Phi squared scales in two and Phi cubed scales in three dimensions, well, what are those fourth, fifth, and sixth dimensions in the Gothic cathedrals doing? Are they possibly bringing that higher dimensional geometric forms into our 3D reality? So what George Leoniak has done, we met about a year and a half ago. He's just an amazing drawer of sacred geometric forms. And he drew this first diagram based upon the findings that I found in the Gothic cathedral steeples. So he's essentially taken the slant angles, which correlate to the six apex angles that I've derived, and he put pyramids or built those in, but he did that based upon the drawing of what is called golden ratio circles. So if you start with that dot in the middle and then go to or start with the inner circle, each of the circles radiating out from it, the diameter is increasing by the golden ratio, just as we showed in our demonstration of how we got the 76-345 geometry. So essentially, if you have the ability to perceive this, you can see those concentric circles as either a cone with the top, closest to us, or that we're at the bottom looking, up into the top of that cone. But no matter which way you perceive it, we've got a cone which has that 76-345 geometry, which seems to indicate that there is a relationship or a scaling relationship which allows for this redimensionalization, I guess you'd call it, of these higher dimensional geometric forms into our 3D reality, and it all seems to be based on this Phi cube geometry. Now, we don't have a lot of time to go through this, but this is perhaps one of the best ways to try to understand hyperdimensions. What George did, he did this all the way up to the 11th dimension, but we're only showing 6 here because if you notice on the bottom right-hand corner, when you get to 6 dimensions, the drawing itself becomes so dense that it's virtually impossible for you to get much out of it if we go much further. But what George has demonstrated here is that when you start with hyperdimensional geometry, if you reorient your perspective to a specific point in 3D space, you're going to be able to reduce that three or four, 5, 6 dimensional object into the next lower dimension. So let's pick, for example, just to give you a brief understanding of this, let's look at the 2D example here. If you see where my cursor is, in 2 dimensions, he starts first with a dot in the 0 dimension where my cursor is. Then when he adds 2 dots, you get a line, and that creates 1 dimension. And then you double that, you have 2 lines, which you then 2 sets of 2 dots, which you connect to make a square. And you use that basic system to continue this multidimensionality. But let's start with the square. If you can visualize that, you can make that square into a single line simply by flipping that up 90 degrees into the air, keeping one end on the ground and flipping the other one up 90 degrees. You're going to be able to convert that into a 2-dimensional line. And then if you flip it upwards, you're going to be able to make that 1-dimensional line into a 0-dimensional dot. Now, to use the same idea with the 3D, you can see that in 2D form, what was a square now from a slightly different perspective is viewed as a diamond. And in fact, the hexagon that I'm pointing to right now is not actually a hexagon, or it can be viewed as a hexagon in 2 dimensions, but in 3 dimensions, it's actually 2 diamonds which are connected by 3 horizontal lines. So again, when you reorient that 3-dimensional hexagon in exactly the right way, you're going to get that diamond that we see in the 2-dimensional diagram. And then when we flip that in upwards into the sky and keep one side down, we're going to see that it goes to 2 dimensions and similarly down to 1. So I don't want to belabor this point, but this is really, really important that it's perspective and orientation that George is demonstrating that pulls these multidimensional geometries down into our 3-dimensional experience. So here's another example of this. I saw this in a video from YouTube. It's called A Beginner's Guide to the Fourth Dimension. Uh, the red dot at the top is in this video is a light, and you can see these light streams, beams coming forth. And what's happening in this case is we're taking a three-dimensional cube, which is done in stick figures so that you can see how it works. And we are now projecting that from the vertical plane to the horizontal plane, and we're seeing that that two-dimensional result looks quite a bit different than the three-dimensional cube in 3 dimensions. So, but you get it, that gives you that perspective. Now, if we move that red dot, we could move it up, down, left, right, sideways. We would get totally different blue perspectives from shining that same light onto that three-dimensional cube, so that what we would perceive in 2 dimensions is much, much different. Now here's another example from that same video. We're taking the 4-dimensional tesseract, and in this video, there's actually a left side and a right side, and these are spinning around, and I happened to catch this view. I couldn't get it perfectly, but you can see that the 4-dimensional tesseract is now in 3D form here on the right side, and actually it's almost at the perfect positioning to create the Metatron's cube in the left example. If the orientation was such that the two dots that I'm pointing to were to come together, that would require just a slight reorientation. We'd have Metatron's cube in that example. So you can see where you can go from 4 dimensions to 3 dimensions on the right to 2 dimensions on the left. So that's the concept. Now, we talked about horizontal and vertical perspectives just a minute ago. I want to show you, this is showing you one of the very early relationships I found in pyramid and steeple geometry, that the apex angle of the Giza pyramid is equal to the slant angle of the Russian pyramid. So the overlay over here at the right demonstrates that kind of with the picture. I've just taken the top of the Giza pyramid and put it over where the slant angle is of the Russian pyramid, and you can see how that works. But I want to show it to you now using this very same type of analysis that was used of shadow casting. So what this picture is, we're going to look quickly at how you can change something from horizontal to vertical and the other way around. I drew on this piece of paper. Well, first let's start with the right. On the right, we've got one of Lisa's capstones, looking down at it from the top. And what I did was I drew the Russian pyramid, just as we did in that example earlier, where I drew them together with the same base length. I drew the exact height of dimensions of the Russian pyramid, and then inside the Giza pyramid. And what I want to show you is just how perspective you can, with light coming down at a particular perspective. In this case, we're taking that Russian geometry and we're shadow casting it as a Russian geometry as well, but now it's in the horizontal plane rather than the vertical plane. And then by changing the perspective just slightly of the light source, I'm able to change that shadow casting from the Russian geometry to the Giza geometry. So I'm hoping that you're starting to see this is further back and a little lower down to get the Russian geometry, and it's closer to the top of the pyramid and higher up to get the Giza geometry. So it's just a question of perspective. I showed you earlier also how the Giza pyramid will, on its side, will generate that angle of 76,345 because it's showing up in the apex of the Giza pyramid. Now, this object that's sitting on the table is actually a hat pyramid that the Pyramid Spiritual Society makes for adherents, and it has the Giza pyramid geometry, but you can see that when we put it on its side, that it's going to shadow cast the angle of the Russian pyramid vertical angle. Now we can do the same thing with the Russian pyramid. Here's Lisa's capstone on its side, and we can put it on its side, and it's going to shadow cast that very same geometry as well. So we've seen now side perspectives and horizontal and vertical perspectives, how this can change. Now I want to just show you a very, very important concept that I found that we'll be discussing here in a moment with the steeples that are on the Gothic cathedrals. Now all I'm doing is a direct shadow cast in the horizontal plane, or excuse me, well, doing it purely horizontally. So this is a cone which has the 76-345 geometry. You can see that you can shadow cast that, and it will shadow cast the same angles and as a four-sided Russian pyramid. And here's the same photo with Lisa's capstone, shadow casting directly into the Russian geometry. And here, this is we're going to talk about in just a minute. This is a six-sided steeple. And I noticed this when I was measuring all of these steeples, that I was very, very concerned that I was making a mistake initially, because I knew the height was right. But what I didn't realize at the time was that a six-sided steeple can have the very same dimensions as a four-sided or a conical steeple can as well, if it's looked at and shadow cast from the proper perspective. So we're going to get into that here for a minute and explain this. I want to explain why the six-sided steeple is so different than the four and the cone. But to do that, I want you to understand face views and edge views for a minute. Now, to use the Giza pyramid, when we look at it with the two sides being parallel to our line of sight, that's called the face view. But when an edge of any pyramid is coming out in front of us like this, directly in front of us, that's called the edge view. Now, the reason why that's important is because you can see the yellow line here, that slant angle or slant height, excuse me, that's the edge. When you can see that's on the side, which is going to be parallel to our line of sight, whereas the edge view and the edge angle are actually going to be, from this perspective of the edge view. You'll see why that's important here in just a minute. All right, Gothic cathedral steeple design. Interestingly enough, only conical, four-sided, and six-sided structures are used to create the steeple design of the Gothic cathedrals. And that's important, as you'll see here on this page. While measuring the steeples, an initially troubling observation on my part was the fact that the very same angles kept showing up no matter which geometric form I was measuring, whether it was a cone, a four-sided, or a six-sided steeple. Now, if you look at the bottom left-hand corner, you'll see a conical conical steeple and a four-sided steeple or pyramid. Now, if that four-sided steeple were pointed the way it was in the previous photos with the face angle, the slant angle of both the Giza, of the four-sided and the conical structure are going to be exactly the same. However, as you look at the six-sided steeple diagram that's here, we know that one side is going to always is always facing you from, if you're looking at it from the front. So we're always going to have two sides, one side that's directly facing us, two sides that are to an angle, but there are no two sides that are ever going to be parallel. So we can't measure that slant angle. We can only measure an edge angle. And so we're really not measuring the same thing. So how was I coming up with the exact same angular measurement with the edge angle of the hexagonal steeple that I was getting with the slant angle of a four-sided or conical steeple? Well, the answer turns out to be, and I know this is getting geeky, but the slant angle of a four-sided steeple is equal to the edge angle of a six-sided steeple whose base is half that of the four-sided steeple. That's a mouthful, but it was something that I just happened to chance upon, and it's just showing again that they had this profound understanding of this geometry and how it would shadow cast. But to show you from a mathematics standpoint how that works, I've got these two samples of the geometry that's showing up. In the first case, we're going to look at the four-sided steeple. Four sides, we have a base length, well, let's start with the height of 9.776. Let's go over to the six-sided steeple. We'll see that we've changed that to six sides, and the height has remained the same. However, what has changed is the base length. The base length went from 4 3/4. I cut it in half to 2 3/8. And what did we find out when we do that? We'll notice that in the four-sided case, the slant angle of 76,345 appears, but in the six-sided case, the 76,345 shows up as the edge angle. So really what this is demonstrating is we're changing our perspective in the horizontal plane in order to see that to measure the edge angle. But when we do that, if we change the height by or cut it in half, we're going to get the same shadow cast projection as we would with either a conical or a four-sided steeple. So that is profound understanding, and they've obviously shown that to us to get this hammered home to us, in my view. So now to kind of go through the math again on that, from this perspective, again, the side length, base length of Lisa's capstone is 4 3/4, and that's the same as the diameter of the cone that I built to do these exercises. So they're the same, but the side length of the six-sided steeple is 2 3/8, or 1/2 that of the four-sided capstone. So I know that there's going to be a lot more for us to look at as time goes on. These are, I think, just the beginnings of our ability to look at this. We're going to try to be taking George Leoniak's diagrams. I see in my head that if they're swirling in a vortex, that it may be possible with enough a study to be able to figure out how to take this orientation or perspective in three dimensions. And a long-term goal would be to actually be able to map how those multidimensional objects come into three dimension through changes in perspective, and hopefully ultimately relate that to the spiraling of the torsion fields inside the pyramid. So got lots of stuff to go on to research here. One of the key things that we were able to get over the Christmas vacation, I just wanted to say we've got a pyramid calculator now. If any of you are interested, that's really so much more powerful than what I had available to me in the past, which was the 1728. In order to use this calculator, you can only change the number of sides, the base length, and the height, which makes holding other things constant a whole lot more challenging. But over Christmas holidays, Christian Herney, who's a PhD student in math at the University of Missouri, contacted me, and I told him of my need to be able to get a calculator with a lot more flexibility to let me hold angles constant and then look for heights, or but just to give me that flexibility of not having to iterate to solutions. So he built this. I've got this available. If there's anybody out there who is interested in doing this kind of work and helping us out, I've got uh, someone who's working on this now. But if you're just interested in having this and checking it out, just give me call me or send me an email at Charlie@Stargate Pyramids. But I'm going to hold out the same discounts that we gave to the folks, in Cincinnati. If you see this and you're interested in buying pyramids or accessories from Lisa at Pyramid Surge, use BSME20 for 20% off. And, here's our contact information. You can contact me at Charlie@Stargate Pyramids and Lisa at Pyramid Surge.
You could have used a better picture there, Charlie, for me.
Well,
My word.
I guess so. Anyway.
Looks like a mugshot.
Yeah. Well, I'm sorry about that.
I'm finally able to hear you about an hour into the session because I got rebooted.
Oh, well, good. Yeah. So I think we're done now. We're done with the slide presentation. So
okay.
If we have questions, I know there was a lot to go through here, and I just want to tell you, all of this is not, you don't have to get it all the first time, but the key takeaways here, there's a Power of Phi geometry that exists in the Gothic Cathedral steeples. We never knew about any of this stuff before, and now I've been able to demonstrate that it shows up in architecture worldwide. So, and even in contemporary architecture. So, fascinating that this has never been figured out before, but it also looks like, and this is going to be the real pizzazz is going to be to try to relate these hyperdimensional geometries and try to see if these higher, steeper pyramid and steeple geometries that we found actually have a role in bringing those higher dimensions down into our 3D experience. So
yeah,
I hope that was helpful.
You see them everywhere you look. You're going to see these pyramids.
That's right. Yeah. Once you see this, you cannot unsee it. You're going to see that the world truly is an open air museum of sacred geometry and golden ratio architecture. So
yeah, and for some reason, I don't know if it was my internet connection, but when we went live, it didn't go live to Rumble. So we'll have to upload this video to Rumble afterwards, but it will be posted there as well. And then just to touch real quick, since I wasn't able to talk earlier for the announcements, I am offering an expo special as well, where I have some products that are 44% off right now.
Oh,
Expo extras. So people can go to my website and find that link. And then next week on Tuesday, at 1:11, we're having Tomas Mueller. So he's coming back and he's going to have a really exciting talk as well. Let me see here. He's going to be talking about the role of color in SCHH hypnosis sessions. For example, how color relates to trauma and how it affects energy centers and allows low frequency entities to come in, earthbound spirits, etc., like that. So mainly when someone experiences a trauma that causes a sad or low frequency emotion to be felt, it distorts the frequency of light in the corresponding chakra. So he's going to talk about that. So I thought that'd be pretty cool. But if anybody has, I don't think anyone has any questions, Charlie. I haven't seen any
Ah!
questions yet.
That means I overwhelmed them.
Probably. Well,
I know
Charlie,
there's a lot of stuff there, but yeah, go back and look at it. And if any of you have questions, just contact me and I'll be happy to answer. And there's a lot of information to take in there.
yeah, Charles Milligan said, "Very cool. Thanks. I'll be rewatching this one."
Yeah, yeah. So anyway, all right. If there aren't any questions, I guess. Do you have any closing comments, Lisa?
Nope. Nope. I'm good.
All right.
Sayonara, everybody. We'll see you next week, I guess.
All right. Have a good day.